So there is this MIT course called as missing semester. So what I would suggest is, this you should look at this thing, okay, especially the one on version control. Please do watch this, and also shell tools and scripting. I didn't actually watch, but from what I heard, these are very good. So sharing the link. Missing semester. Yes. Yeah, great. So in this week, definitely you should all be very accustomed to using Git as computer scientists. So please do, and no, many times we use it without having a good understanding about it. But if you get a good understanding about this version control systems, you will be able to do very, yeah, you will become a powerful engineer. Also, shell tools and scripting also you may learn in your course, but this week itself we can make some good progress on shell programming and version control. If we can do these two things, then it will be nice. Other things also could be very interesting. I didn't look at them. Meta programming. Make files. Yeah. We learned about make files, na? So you should learn about these make files, how these make files work, and okay, nice. Okay, I think my suggestion is, in this, to go through all these things. High priority meta programming is important. Version control is important. Shell tools are important. So you will become very ninja computers science engineers if you learn these things. Okay, so now let's get back to what we are doing. So today my scribbling pad is in office, so I'll mostly be typing, but it should be all right. Today's session primarily, we will review the ideas that we have seen already, so that it's a kind of like a warm-up class, and tomorrow we will try to look at STL. STL also we looked at little bit in the last class of the computer programming course, but we'll try to take a deeper look at it maybe. Okay. Okay then. So now let's today we'll review generic programming one more time, and from there we will move forward. Okay, just give me a minute. Okay. So what do we do? So let's see. 1 minute. Share screen. I think maybe I can just, yeah. Okay. I hope you are able to hear. Okay. So you're able to see the screen, right? Okay. So, like we have, I guess we have seen this before. Let's say we want to write a function in C++ to compare, to data types. Not to data types. No, you want to compare two values, and yeah. So in order to compare, so we want to compare two. If you want to compare two integers, we can say int v1, int v2. Just 1 minute. Yeah. So if you in usually in C, we would like to pass. Want to take this opportunity to review some of the ideas comparing and contrasting C and C++. The function signature, if it is in C, it will be like this. Okay, so you have you're passing two values v1 and v2, and yeah, so you compare if v1 is greater than v2, then maybe I can use this. If v1 is less than v2, then return -1. If v1 is greater than, or yeah, if v2 is less than v1, return 1, else return 0. I would like to have Control Shift I. So this is the way we we write a compare function in C. Well, the one problem, like the parameters are passed using call by value in C. They are passed call by value in C. So this call by value, oh, okay, if v1 is greater, okay, thank you. So this passing call by value, it is for integers, it's not a big deal. But if you look at, like, for example, when you're passing a structure or a bigger data type, or a data type which involves like maybe 8 bytes, 20 bytes, things like that, then it is going to be an expensive proposition, this copying passing data using call by value approach is expensive. So in C++, we can pass them using a reference. So when you pass them by using a reference, now instead of call by value, by putting that ampersand, so we are using call by reference. And if you think about it, in this compare function, you don't even want to, you are not even intending to modify V1 and V2, but still we would like to use call by reference for the reason, what's the reason? Because it helps in saving, it saves time, because when we use call by reference, there will be, we just pass the pointer, although copies are not made. Yeah. So Gnan Prakash has nicely summarized it. Copies are not made, only the reference is passed. So that's the advantage using call by reference, and it may not be such a big deal for integers, because the pointer and the integer, the number of bytes required for a integer value and the number of bytes for a pointer could be the same. So it may not be such a big deal here, but this will be of advantage when the data that is being passed as parameters, it requires a greater size. And but then when we write programs, we don't want to unnecessarily cause scope for introducing bugs. That is, no, we don't want, we know that in this compare function is not supposed to modify V1 and V2 anyways, and we don't want it because of some programmer inadvertently modifying V1 and V2. So we put this keyword const before it. So when we put this keyword const before it, then what happens is, if you try to modify, then let's say if you say something like this, then the compiler will throw an error. The compiler will throw an error. Okay, so let's see what mean. So cout less than compare 10, 12, and new terminal cd cpro g++ compare.c. What is the issue? You have to use using namespace. See, error assignment of read-only reference. So by telling the compiler, this is all these things are very, very important in documenting your program. Okay, so const, when you write this function, make this put these keywords explicitly, you are documenting your function for your own self. Down the lane, when you, after a year, when you look at the code, immediately all that signature tells quite a bit of information about the function you have written, and it helps others also. Like someone else is trying to read the code and want to modify the code. When they look at these keywords, then they will understand the intent, your intent. Third, it helps the compiler also. When you make mistakes, compiler will catch the mistakes. Okay, so here on line 14, you are trying to modify V1, so the compiler throws in. Okay, so let's see. Shift I. See, minus. So 10 is less than 12, so -1 got printed there. Let's try to have Okay, you're all with me so far here. So as I told, today is a review lecture, review for me and review for perhaps for some of you also. So now let's see, we want to compare two strings. Okay, and in C, we have this string data type that is available for us. So which is very, very advantageous for us. And that's all. So on strings in C, we have to use, string compare operation we have to use. But in C++, you don't need to use string compare operation. This less than operation, greater than operation, they are overloaded. Okay, so operator overload. So operator overload. So when the two operands of less than or of type string, then what happens is an equivalent of string compare function will be invoked underneath. So yeah, so that's what we do. Everything else remains the same. And like for example, here you can the other thing we can do is so string so S1 so let's say Signan Prakash and S2 maybe you can have sure. Okay, so now we can say compare S1 comma S2. So one interesting thing also you can see that we have two compare functions. There are two functions with the same name but different signature, but the compiler, depending upon what is the kind of operands, what is the type of operands that we are passing to the compare function, the appropriate function call will be made. All right. So maybe see out compare, maybe test. So this is what do we call this one? So when two functions with the same name but different parameter types or function signature, based on that it's called as overloading. No? Okay. What is polymorphism then? So G++ compare.c, you can see that Nana is less than Shivam, so -1. And in the next case, one is since functions act differently to different objects. Okay. Yeah. So, and then here finally we are passing two strings test. Overloading is a type of polymorphism. Okay. I see. Thank you, Harshit. Are you all with me here? That what's going on? So, but the thing here is we are not happy with this. And then later, let's say if you want to have float, if you want to have float, then again we have to introduce float, and then again we have to introduce float like this. In fact, for as a part of programming for performance course, I'm trying to write some matrix operations related to matrices and vectors. I have the same problem because you can write a whole set of library for matrices on vectors where elements are of type floating point numbers. But then there could be some other application where they want the same set of things, but with but the elements, the application requires the elements to be of type double. then the whole code base need to be copy pasted. And if you make one change in the code base, like let's say you have a different matrix vector multiplication algorithm. If you modify that algorithm, then you have to go to the other code base, which consists of which handles double precision numbers. So it becomes quite a pain. Okay, so this is not quite the right way to go about solving this problem, where the algorithm remains the same, but a certain primitive operators, the way we define certain operators on the domain data type is a bit different. So so in order to solve this problem, so we try to write generic programs. Okay, so in generic programs, what do we do? So generic functions. So we say template. You have to use templates. Template class T, and then that's it. So now we don't need this code. All this code okay, great. And let's see if this program compiles now. I hope you're all with me. So we are just adding this template. I think we don't need semicolon there. So we are writing a parametric compare function. And the parameter here is T, which indicates the type. Awesome. So see, so now we have only one version of the code. The important thing here is when the compiler looks at this function 31 to 39, it will not be able to generate machine code for execution, because in order for it to generate machine code for execution, it needs to know whether the data types of V1 and V2 or integers or floating point numbers, whatever they are, the compiler needs to know. No, we cannot use auto, Abhishek. No. Auto, we'll talk about auto later, but auto doesn't serve this purpose. Auto doesn't. So since Abhishek brought it up here, so usually, like for example, we say int v is equal to 10, but instead of this, we can use the keyword auto v is equal to 10. So the compiler looks at the right side of the assignment, and it knows it's an integer. From that, from the right side, it infers the type of the variable v should be an integer. This will be useful in the next class when we talk about STL. There auto will come in handy, because remembering the particular iterated data type, etc., is a bit of a pain. So if you use auto, life becomes a bit easy for you. But here, the important thing here is type inference from RHS, and inferred type is passed on to LHS. Yeah, that's true. After line 46, we will be assigned int data type. That's true. And in fact, some of you who are familiar with Python programming, Python does a lot of automatic type inference. It will be treated as an integer, Prakash. Okay. So, well, yeah, the import, yeah, so we are, that's true. It has to choose the data type during compilation. Unlike in Python, very good point, Tejas. So there is in Python, so Python versus C++ type inference. So in Python is what is called as a dynamically typed language. Dynamically typed language. That means the variable types can change during as the program executes. Whereas C++ is statically typed language. I'm going to, so there is a very important thing. What if you write V is equal to A at line 50? Why, how is it possible? Where, what is A? Yeah, it will become character type. Okay, yeah. So, yeah, understood. So you will get a, let's try, good idea, like why not? So maybe compiler will complain. Let's do this. G++ compare.cc. Well, the problem is, this ASCII value of that will be assigned to that through through type implicit type conversion is happening there. Maybe we can try to do 10.3 if C++ compiler. Yeah. So C++ is doing automatic implicit type conversion. Yeah, that's true. 10.3. We can do a string assignment, but I'm not happy about it. I don't know whether to. Yeah, invalid conversion. Yeah, okay. So this is 10 as it treated as a string. It is saying, you're trying to convert a const can star to int. Okay. So you can at least see from here that the compiler thinks of V as an integer. Are you with me here? Yes, no? But in Python, this is perfectly fine. Python just changes the data type of V from integer to string on line number 51. So how many of you know the difference between interpreted languages and V is equal to 10.3, then we will store 10. Yes. So how many of you know the difference between interpreted languages and compiled languages? So in Python, there is no machine code that gets generated. There is no machine code. So here in G++ compare.c, compare, if you do file a.out, it's an executable file. And so what happens is yeah, let me do one thing. I would like to take this opportunity to tell one nice idea, and then we will move on. Maybe A3. So as I type in, I will answer Abhishek's question. Abhishek, C++ is nothing like a open source. There are C++ is a standard, and there are different compilers. GCC, G++ is one compiler, and G++ compiler is open source. That is, you can look at the G++ compiler source code and know see how the compiler for C++ programming language is built. But there are commercial compilers, like for example, Intel C++ compiler. It is not open source. Intel C++ compiler, it is closed source. Intel doesn't wouldn't like to release its compiler source code to us. Are you with me here? Make sense? There is a reason why I am showing this to you. Yeah, so maybe there's a very important point I would like to show through this very small example, but still it illustrates. Yeah, maybe I can use G++ minus G add dot cc obj dump minus d minus s a dot top greater than add dot emp control rule. Okay, so now I would like you to look at this code. You know, like from on line number 396, you have A3 is equal to A1 plus A2. The next four instructions, they correspond to the assembly language instructions which are equivalent to that A3 is equal to A1 plus A2. And this assembly language programming you will learn in your computer systems organization course. What I would like you to note is the instructions to execute, the instructions to execute assembly language to add integers is different from the instructions required to add floating point numbers. Okay. So what is the point here is, the point here is if you don't know if the compiler doesn't know the data type of the variables, the compiler will not be able to generate the equivalent instructions. Like for example, if it's addition, it has to use integer addition operations. If it is floating point numbers, it has to generate floating point add instructions. And in the so on and so forth. So what happens is the compiler, if it doesn't know the type of the data at compile time, it will not be able to generate the instructions. So here on the, when you look at this template code, when the compiler looks at this template code, it will not be able to generate equivalent instructions because it doesn't know what instructions it should be using to compare these V1 and V2 variables or V1, so on and so forth. So what happens is only when you make a call such as this, the compiler instantiates the compiler. When the compiler looks at this, the compiler knows that you are calling the compare function with two integer parameters. So it generates an integer version of the compare code. Are you with me here? That the compiler generates an integral version of or an integer version of your code. And if you later on down the lane, if you use floating point, like for example, now if you make it something like 10.0 and 12.0, so when the compiler generates code, the compiler generates three different versions of no, I want to make a difference between Python and here, Dhruvan. So here, the compiler generates three different versions of the compiled code. One is the floating point version or the double version. Okay, so see, you can see how it changes. Actually, this is equivalent to this. No, this is automatically this gets like for example here. This is also both these, we can invoke it like this or like this. So here you can see the function signature when I hover the mouse or compare. This is the particular function that gets invoked. And here if you see again, this is the particular function that gets invoked. Well, okay, so So are you with me here? 3 different versions of compare function are generated, and all integer calls will go to the integer version, all floating point calls will go to the floating point, all can we check which version is so these functions are actually created on the hard disk. Samoga has this nice question. Let's do this. I never did this one, but let's g++ minus g. Let me use g++ minus s compare.cc. So here, yeah, I'm not able to make out this code, but how do I see compare dot section dot size dot text compare? These functions are created not in the memory, in the hard disk. Let's try to do it in a different way. Obj dot minus d minus s dot out greater than compare dot d. Okay, at least what I can tell you from this here is, here you are making a call to some function, and then this function call is different from this function call, where we are trying to compare two integers. At least this much are you able to observe, that we are trying to call different functions names. This is call queue followed by, there is some function name here, so they are different for integers. S1 and S2, Z7. Compare. Yeah, so when you are comparing strings, so let's do one thing. At least one thing you can notice is call queue F47. F47 is the address of that function which compares two strings, and F06 is the address of that function which compares two integers. So you can see different functions are called. Are you satisfied to some extent? I'm just trying to convince you without completely getting into the nuts and bolts of these things. All right, yeah. So now, what's the story is the C++ compiler, it needs to know the type of every variable at compile time itself so that it can generate appropriate code. But on the flip side, Python is an interpreted language. It doesn't generate any code. Okay, so when Python looks at a particular instruction, A1 plus A2 at the runtime, and at runtime it figures out, hey, A1 and A2 are floating point numbers, and so I have to call a function which does floating point addition. So since that is possible, because Python doesn't generate any code, it interprets. So when it interprets, what happens is, at the time of interpretation, Python looks at the data types and it figures out this is the particular operation I have to do. Let's say if I'm so think of it this way. Let's say you have to write a function called cut vegetable, and to the cut vegetable function, you can present an orange or an apple, the way you cut orange is different from the way you present, you cut an apple. So in the case of C++, which generates the whole thing well in advance, it needs to know, so you cannot tell a cut apple function to cut an orange. It doesn't work. Okay, the C++ function needs to know, C++ compiler needs to know whether you want to use that particular function to cut an apple or an orange. It needs to know. But on the contrary, Python at the time of presentation, it looks at it and it figures out, hey, this is an apple, and it uses the knife to cut the apple. And if it looks, if the fruit that is presented is an orange, then Python interpreter will use a peeler and peels the orange. Okay, because it's not going to generate any code, it interprets things. Okay, so important idea. So in Python versus C++ type inference, Python is a dynamically typed language and interpreted, and C++ is a statically typed language and compiled. So it needs to know all the information at compilation time itself, all the data type information it needs to know at compilation time itself. Okay, great. So now, so we would need this template or generic programming not only for functions such as this, when we are working with classes also. Okay, so let's say we would like to now write a program called as pair.cc. Yeah. So just 1 minute. So we'll write one. So we want to write a. We want to have a class which consists of a tuple. Okay, let's say it consists of a tuple or a pair. So class pair, class pair, or it can be a tuple, and it has two, like this is the idea of data encapsulation. There are two elements here. Let's think that these two elements, let's call them as int first and int second. And so there is a public part. So no one will be able to access first and second variables. And yeah, so I think we don't need, this is an empty constructor, or maybe we don't need a constructor, we can just leave it as it is. But then we will have get accessor functions. We can have get first function, which returns first underscore. Okay, and get second. Similarly, we have return second. Okay. See, this is these are the. We also need, of course, set functions. Void set first. And yeah, for the sake of simplicity, let's say first. Okay. And then we need a swap function. Void, let's say we need a reverse function, reverse. So when we call reverse, what happens is int temp it says no, temp is equal to first is equal to second, and second is equal to first. Are you all with me here? This code makes sense for you? I hope there are no problems here in this code. Line 16 should be, oh, okay, it should be temp. Line 16 is temp. Okay, great. So now we have pair P1. Maybe we should have a constructor, when, so that, what is the syntax for the constructor? Index int y, there is an initializer list, na? Can someone tell me the initializer list approach for constructor? Something like this we have. I forgot. So that way when we do print cout less than p1 dot get first, p1 dot get second. Do you think this will compile? G++ a.cc using namespace std. Awesome. Main must return an int. Okay, main is still haunting this return type of main. So here I think this should be like this. That is, this first is copied. So this, remember this, whatever this parameter is passed is copied to the first underscore, the local variable. So here this is what is called as an initializer list. Okay. So we didn't put space in between, but you got it. Are you all with me here? (10 and 20), and then we say p1 dot reverse. See, 1020 has become 22. So nothing surprising, but just want to tell one more thing also here. You can, if you want to take a pointer approach, pair pointer is equal to new pair 100 comma 200. We can do this also. And then, so remember, once we have the pointer, let's say, how should we invoke it? How should we invoke each of these things? PTR. I want you to understand this. This is a very important thing, that this is very similar to C. So if you get a pointer to an object, then this is the way you will be accessing things. Are you with me on this one? This syntax, that there's a difference between P1 and PTR, pair star PTR. Okay, PTR, when you do using new, memory is allocated from the heap, but when on line number 29, the way the memory is allocated, the way, and the scope, the lifetime of this P1, it will be over after main is over. But in general, when main is over, then it doesn't matter. But if you, generally speaking, if you allocate memory via heap, even if you come out of the function in which way you have allocated memory, that memory still remains until you do an explicit delete. This is equivalent to our malloc and free. New is like malloc actually. New is like malloc. P1 is not allocated memory in the heap. I don't think so. It's allocated memory on the stack. It's a local variable. Are you all with me? Do you see the difference between line 29 and line 30? I want to make that point very clear to you. All good? Now comes the story. If you want to store, now we are storing a tuple of integers, but if you want to store a tuple of floating point numbers, what do we do? Then do we have to repeat the whole code again? It's a painful thing, right? And this is what happens when you, in your data structures course, when you write a linked list code which can handle some data type like integers, and then let's say if you want to use the same linked list to handle some other structure type or some other kind of data, then you have to rewrite the whole code again, and that whole thing becomes very problematic. Do you see the challenge here? Do you see? Because a linked list of integers, a linked list of floating point numbers, a linked list of strings, theoretically speaking, all the way the linked list logic is the same, but just the data payload is different. Just because of that, you will end up writing a code for this linked list for different data types again and again and again, and that's not the right way to engineer your software. So what do we do? So we use templates here. We want to change this code. So class T. So we, and then wherever there is int, we would like to T great. Now let's see if this works, the same code. Delete PTR. Okay. So here to start with, since we have used, we should use this one. And I'm not sure the syntax for this. Maybe this should work. Let's see. New pair. Maybe should we use int? Can someone tell me the syntax for this? Oh, okay. I think we should use maybe not here. Yeah, awesome. Good. See, it worked. So now, what I would say is, like, for example, we can even have pair string p2. Yeah, so let's use Yash and Akshit. Easy to compare their names. One comes at the end and one other comes at the beginning. So now you can print C out less than p2 dot get first. Oh, why I can have the same thing? So now you can see the whole thing works just for strings, just like. So this is the idea that you have learned in this particular example. Let's comment on the other code. We don't need all that code. Are you all with me here? So we are now just looking at this code, which works only on strings. Oh, I did to do p2 dot reverse. Where is it? Temp. Okay, okay. See, nice. Do you see the error? Okay. Thank you, Ish. We don't need string copy because equal to is overloaded. I'm thinking it should work. Yeah, done. Awesome. So the point here is you can write parametric classes also. Okay, you can write parametric classes. So you can write a parametric class for linked list. You can write a parametric class for trees, parametric class for you know, what do I say, graphs, and you can use the same thing for different kinds of data types on different kinds of data types. Are you all with me here in today's lecture? So in the next class, we will look at STL, and STL, of course, is a generalization of this idea. What I would say is the way I would like you to learn C++ so that you will be able to build the STL library by yourself. Okay, that is the goal. That's one. Second thing is, second important, so that we will learn next week is inheritance, interfaces, etc., abstract classes, etc. There, what happens is you will have an abstract class which provides insert, delete, search operations, but different people can realize these insert, search, delete operations in different ways. Like, for example, in your data structures course, at one point you may realize these insert, search, delete operations using what are called as red, black trees, and later on you can have a different realization of the same, and you can use AVL trees to do it. And later on, you can have a different realization where you can use perhaps B trees to do the same. So the same interface, abstract interface will be there. Abstract class will be exposed to all the end users. but internally you can have different implementations for this abstract class. So there the idea of inheritance comes in very handy. So the plan for tomorrow is we will study STL number 1, and in the next class and the next week's class we will start with the inheritance. Okay, so that's all for today's class. Just to kind of finish on Akshit's question. So Akshit, you can see the first here, na? The first and second without underscore, they are parameter names. They are the name of the parameters for the constructor pair. And first underscore and second underscore, they are member variables of this class. They are member variables of this class. They are and this notation means usually what we do is, instead of writing it this way, so I will tell you what happens. Constructor gets executed whenever this object is instantiated. It's like when you give birth to a baby, you do some basic bookkeeping stuff, right? And that's what the constructor does. So this is the actual code. What we have written, C++ provides a shorthand for this. Second. And we don't need this. So this is the constructor code. So here on line number 35 and on line number 36, when you create new objects, then the corresponding constructor will immediately be invoked. And here first will be equal to 10 and second will be equal to 20 on line number 35. And on line number 36, 100 and 200 correspond to first and second. And we use these values to instantiate. Line number 10 is required. When we have an initializer list, this is required. So this will be assigned to, we are copying first to the first underscore variable, which is part of the class. The first here corresponds to the parameter, the first underscore corresponds to the member variable of the class. Are you all with me here? You understood the constructor idea, na? There is also a destructor, but in this particular case, we don't need the destructor. Destructors are required when you are working for different, for many of the data structures that you work with, you do need destructors. We will talk about them in a later class. Okay, so that's all I have for you today. So, well, very happy to see you again, and we will continue. So